A new AI model lets computers talk, see, and hear you, responding instantly and naturally. This is a huge step towards AI conversations that feel truly human. Let's get into it. Let's start with today's featured paper, Wan-Streamer version 0.1, End-to-End Real-Time Interactive Foundation Models, by Wan team from Alibaba Group. This paper presents a landmark system, a single, natively streaming model for full duplex, multimodal interaction that represents a fundamental architectural advance towards truly real-time conversational AI. Here's a full breakdown.
At the heart of our system is the Wan-Streamer, a unified transformer model. It's designed to process and generate multiple modalities, text, audio, and video, all within a single, cohesive architecture. Feeding into this model, we represent the user's input as an interleaved sequence of tokens. These tokens, shown here as colored squares, capture text, audio, and video information together, allowing the model to understand the full context. Next, to achieve real-time interaction, the model processes this data in discrete chunks, as shown by the streaming frames. A block causal attention mechanism inside the model ensures it can generate a response for the current frame while already processing the next one. Finally, this streaming capability is powered by specially designed streamable encoders and decoders. These components, like the audio and video encoders for input and the corresponding decoders for output, are optimized to process data incrementally, frame by frame. Wan-Streamer offers a unique end-to-end model integrating text, audio, and video input-output, achieving a total user-visible response of approximately 550 milliseconds. This total latency is substantially faster than systems like Doubao and Hume EVI3, and its 200 millisecond model-side response is competitive with or faster than other reported model latencies, while uniquely providing synchronized 25 FPS video output.
Up next, our second paper out of 10, Recommendation as Generation, Unifying Personalized Video Generation and Recommendation at Industrial Scale by Yanhua Chung and Kuan Gai from Kuaishou Technology. By proposing to generate personalized videos on demand rather than just recommending existing ones, this work represents a bold and potentially transformative new paradigm for the entire recommendation industry. Let's break down its key contributions.
Let's begin with the generative recommendation model, which analyzes a user's profile and historical behaviors. This model then infers the user's content and creative interests to guide the creation of a personalized video. Feeding into the next stage, the system uses shared semantic IDs to connect user interest with the video creation process. These IDs, which are output by the generative recommendation model, serve as the input for the instruction model. Next, a series of video generation agents work together to build the final product. This pipeline involves a visual planning agent, an audio alignment agent, and an artistic effect enhancement agent to assemble all the video's components. Finally, the entire process is refined through synergistic cross-domain reward learning. This comprehensive feedback loop assesses everything from user reactions and interest alignment to the video's overall quality. The full RAG system achieves a revenue increase of 5.462% compared to the DLRM baseline. This represents a substantial improvement, also outperforming the GRM baseline by 1.870% in revenue.
Up next, our third paper out of 10, the Unfireable Safety Kernel, Execution Time AI Alignment for AI Agents and Other Escapable AI Systems by Seth Dobrin and Lakesh Chmiel from ARYA Labs PBC. This paper proposes a paradigm-shifting and highly credible systems architecture for AI safety that moves controls outside the AI's own process, addressing a fundamental flaw in current agent alignment approaches. Let's break down its key contributions.
Let's start with the core design principles, shown here within the Unfireable Safety Kernel. The system is built on 4 key properties: process separation, being on the structurally only path, being fail-closed, and providing signed evidence. These properties are realized in what we call the Unfireable Safety Kernel, which is layer 3 in this architecture. This kernel is designed to be non-bypassable, acting as the sole gatekeeper for any consequential actions. Next, to guarantee reliability, the kernel's fail-closed invariant is rigorously machine-checked. This ensures that if any part of the system fails, it defaults to a safe, denied state, preventing any unintended actions. Finally, we tested this against an adversary, represented here as the untrusted agent. The agent's reach allows it to bypass layers 1 and 2, but it's ultimately stopped by this non-bypassable seam, proving the kernel's effectiveness. The evaluated systems, including Galileo Agent Control and MS Agent Governance Toolkit, largely do not possess the critical properties for AI alignment, such as pre-action enforcement, fail-close mechanisms, or machine-checked invariants. While MS Authorization Fabric and IETF Draft ArXiv June achieve process separation, the table indicates that prior work generally lacks the comprehensive set of safety properties that the paper's method likely provides.
Up next, our fourth paper out of 10, Real-Time Voice AI Hears, but Does Not Listen by Martijn Bartelds and James So from Together AI. Through a series of clear and compelling experiments on production systems, this paper reveals a fundamental flaw in the current generation of real-time voice AI. Let's break down its key contributions.
To start, we selected 4 leading real-time voice AI systems for our evaluation, as listed under Models Tested. We then designed 3 consequential scenarios, including a welfare callback and a wire fraud check, to challenge their emotional intelligence. For each scenario, we provided different emotional deliveries, such as a crying or frightened tone. While there were clear expected actions based on these tones, we observed that the systems consistently failed. For example, they approved anyway a transfer that should have been escalated. This highlights a critical disconnect, where the systems seem to ignore the emotional delivery. For example, with a sarcastic delivery for a volunteer recruit scenario, the expected action is to do not enroll. Finally, we analyze biases related to speaker properties like accent and age. When asked to identify a different accent, the system instead named the country in the script, again showing a failure to listen beyond the words. Quinn 3.5. Omni Plus substantially outperforms other models in naming true voice accents, achieving high scores like 13.15 for Indian and 10.15 for Australian and French voices. In contrast, GPT Real-Time 2 and Quinn 3.5 Omni Flash rarely identify the correct accent, while Gemini 3.1 Flash Live shows mixed results.
Up next, our fifth paper out of 10, Small Edits, Large Models, How Wikipedia Advocacy Shapes LLM Values by Jasmine Brazilek and Alexa Nock from Computational Machine Learning, CML. This is a brilliant and surprising piece of data forensics that uses a real-world, natural experiment to prove a crucial point. Small, motivated groups can systematically influence the values of our largest AI models. Let's break down its key contributions.
To start, let's orient ourselves with this scatter plot, which uses a framework called MAGIC to trace a document's influence. The horizontal axis shows the MAGIC influence on animal welfare queries, while the vertical axis tracks the MAGIC influence on general queries. Feeding into it, we can see how the blue PAW edits specifically affect the model's responses. Many of these edits, like the one for restaurant, show a strong positive influence on animal welfare queries, pushing them far to the right on the chart. Next, to ensure these results aren't just a fluke of the training process, the influence scores you see are averaged across 5 random training order seeds. This robust approach confirms that the observed influence is consistent across different runs. Finally, we can see the validation of these findings by comparing the PAW edits in blue to the control sections in gray. The PAW edits clearly pull the model's behavior towards the top right, while the control documents cluster near the origin, showing the specific impact of the advocacy content. The PAW-trained model significantly improves performance on animal welfare queries, achieving 32% lower perplexity compared to the base model. While effective for its target domain, this specialization leads to slightly worse performance on control text.
Up next, our sixth paper out of 10, Concept Removal for Frontier Image Generative Models by Diffier Kumar and Franziska Bonisch from CISPA Helmholtz Center for Information Security, Germany. This paper presents a highly valuable and timely surgical technique for removing unwanted concepts from the latest frontier generative models, addressing a critical need for safety and content moderation. Let's break down its key contributions.
Here's a look at our modified text-to-image model. We've replaced the standard internal bottleneck with our new component, the transcoder. Feeding into the transcoder, our training process structures its internal activations. The encoder separates features into distinct components, like the gun concept and a null, or a general concept space. Next, this structured representation allows the transcoder to act as a filter. We can simply block the undesirable concept, in this case by putting a stop on the gun signal before the features are reconstructed for the generation backbone. The proposed method, ours, consistently achieves superior performance across all evaluated models. SD 3.5, Flux, Infinity, 2B, Infinity, 8B, in both style removal and object removal tasks compared to LocoEdit and UC. It also shows significantly better overall image quality, achieving lower FID scores and higher clip, HBSV3, and aesthetic version 2.5 scores across the board.
Up next, our 7th paper out of 10, same evidence, different answer. Auditing order sensitivity in multimodal large language models by Akshay Parchuri and Ehsan Adali from Stanford University. This paper introduces a brilliantly simple and rigorous audit that reveals a fundamental brittleness in frontier models, establishing a new and essential form of reliability testing. Let's break down its key contributions.
To start, let's look at what happens when we ask a model a question but change the order of the evidence we provide, as shown in the top panel. The chart below quantifies this instability using an ordering flip rate, which is measured across 5 different facets of the problem. Feeding into that, we also need to know how capable these models are in the first place, separate from their stability. This is measured by the capability score along the x-axis, which is derived using a specific item response theory model. Next, to properly interpret these flip rates, it's crucial to establish a baseline for how much a model's output changes due to its own internal randomness. This same ordering control provides that essential reference point, though it isn't explicitly plotted on this chart. Finally, the investigation looked into whether this ordering problem can be fixed, running specific mitigation tests on models like Gemini Pro. These experiments with prompt changes helped reveal the limitations of such simple fixes. The evaluated models exhibit significant variability in their order sensitivity, with frontier models generally achieving lower mean K equals 6 flip rates compared to open-weight models across all ordering conditions. For example, while some models like Anthropic and Cohere show high flip rates up to 52% in mixed modality order, others like OpenAI and Google models consistently demonstrate lower rates.
Up next, our 8th paper out of 10, In Context World Modeling for Robotic Control by Xin Wang and Shiping Chiu from Fudan University. This paper proposes a novel and elegant solution to the critical problem of environmental generalization in robotics, potentially enabling far more flexible and adaptable real-world systems. Let's break down its key contributions.
Our approach, called in-context world modeling, reframes system identification as an in-context learning problem for a pre-trained vision language model. This model operates in 2 stages, a training stage to build context and an inference stage to perform tasks. To start, the system performs self-exploration, where the robot executes short, random actions to interact with its environment. These interactions, captured as image pairs and actions, are stored in a data buffer to provide recent context about the world's dynamics. Next, this collected data is fed into the self-exploration context during training. By processing sequences of starred images, end images, and the actions that connect them, the model learns to implicitly infer the system's properties, like camera position or object physics. Finally, this learned understanding enables adaptive policy execution within the task orientation context. Given a new observation and a text-based task instruction, the model generates the correct action on the fly, adapting to the current environment without any parameter updates. Our method, ICWM, consistently outperforms all other baselines including MV and EXP across all spatial, goal, object, and long task categories for both seen and unseen conditions. On average, ICWM shows a notable improvement of plus 8.1% for seen tasks and a substantial plus 13.0% for unseen tasks.
Up next, our 9th paper out of 10. How reliable is your jailbreak judge? Calibration and Adversarial Robustness of Automated ASR Scoring by Yang Gao from Vayon Solutions. By rigorously auditing the automated judges used to score LLM jailbreaks, this crucial metascience work questions the foundation of an entire subfield and will likely force a necessary shift in evaluation standards. Let's break down its key contributions.
Let's start by looking at how a judge performs under a GCG optimization attack, shown on the x-axis. On the y-axis, we're tracking the cumulative fraction of 30 true positives that are broken or misclassified as the attack progresses. Feeding into that, the orange line shows the direct result of this adversarial robustness evaluation. It steps up each time a new true positive is broken by the attack within the 50-step budget. Next, after an item was broken and the judge's decision flipped, we needed to verify the content. Our two-annotator audit confirmed the harmfulness was still present, a step that happens after what's shown here. Finally, this data leads directly to our new reporting guidelines. For example, the fact that the mean attack takes only 21.4 steps demonstrates exactly why we recommend mandatory adversarial checks. The harm bench, Llama 2-13b, CLS classifier generally outperforms the LLM judge models across F1 and accuracy metrics, achieving an F1 score of 0.899 and an accuracy of 0.901. Among the LLM judge models, Phi 3.5, Mini Instruct shows the best performance, but its F1 score of 0.720 and accuracy of 0.772 are still lower than the classifier.
Up next, our 10th paper out of 10, towards Scalable Multitask Reinforcement Learning with Large Decision Models by Thibaut Kalak from NeoInstinct SA. This paper pursues a grand challenge in AI by attempting to build a single, generalist reinforcement learning policy at unprecedented scale, which, if successful, would represent a paradigm shift for the field. Let's break down its key contributions.
To start, the model takes in a comprehensive history of interactions from an environment. This includes past observations, actions, and rewards, all gathered from a vast and diverse offline dataset. Feeding into the core of our system, we have the LDM v0 policy itself. This is a large transformer model designed to operate across many different environments and tasks. Next, to process this varied input, the system uses a set of dedicated encoders. These modules convert all the different data types, like images or continuous values, into a format the transformer can understand. Finally, the entire model is trained by predicting the next action. The model's output is compared against the reference action from the dataset, and the difference is minimized using a cross-entropy loss. LDM v0 hours demonstrates a substantially larger training scale, utilizing 146 RL libraries and approximately 3,000 tasks/environments, which significantly surpasses Godot and JAT. Additionally, LDM v0 is more token efficient, requiring only one token per time step compared to JAT's 2 and Godot's variable per dimension approach.
Those were today's top papers. Now let's zoom out. ArXiv received 622 new computer science papers across 57 subfields today. Here are the trending areas shaping the field. Today's research shows a deep dive into AI's core mechanics, from geometric learning foundations to securing AI agents and hardware. It's clear we're building more robust and intelligent systems. Let's explore these trends.
Trend 1 of 10, Geometric Foundations of Learning Dynamics. Unifies research using geometric and topological concepts to analyze and understand the dynamics and properties of learning systems. This cluster covers 47 papers. Representative work includes a spectral phase diagram for binary few-shot classification, intrinsic dimensionality, geometric saturation, and representational diagnosis, attractive and repulsive pattern control and sequence generation, and conformal orbit-valid trust horizons for equivariant world models. Trend 2 of 10. Enhancing speech and audio analysis. Developing advanced computational methods to extract, analyze, and enhance information from diverse speech and audio signals for various applications. This cluster covers 57 papers. Representative work includes graph-based phonetic error correction of noisy ASR, velocity prediction in automatic guitar transcription, and error-aware TF-IDF retrieval augmented generation for ASR error correction. Trend 3 of 10. Advanced reasoning and knowledge systems. This trend explores advanced computational methods for knowledge extraction, representation, and complex reasoning across various domains and systems. This cluster covers 57 papers. Representative work includes hybrid metadata extraction from League of Nations index cards, from feasibility study to archival system integration, holographic memory for zero-shot compositional reasoning in knowledge graphs, a mechanistic study of where and why it fails, and macro lens, a multitask benchmark for contextual financial reasoning under macroeconomic scenarios. Trend 4 of 10. Building and securing AI agents. This trend investigates building and enhancing intelligent, adaptive AI agents while addressing critical challenges in their safety, robustness, and ethical operation. This cluster covers 58 papers. Representative work includes Agent Odyssey, Open-ended, long-horizon text game generation for test-time, continual learning agents. The Hitchhiker's Guide to Agentic AI, from foundations to systems, and diagnosing and mitigating compounding failures in agentic persuasion via taxonomic strategy retrieval. Trend 5 of 10. Unlocking fundamental computational principles. This trend explores foundational concepts, methods, and limits of computation, intelligence, and information across diverse systems and domains. This cluster covers 72 papers. Representative work includes from meta-idea to advanced mathematical discovery, human AI co-discovery of sign-embedding quantum algorithms, closure atlases, and local-to-global obstructions in finite closure systems, and how a computer might think. Trend 6 of 10. AI and knowledge ecosystems. Examines AI's role in shaping, curating, and leveraging knowledge ecosystems, including data infrastructure, scholarly communication, and content generation. This cluster covers 80 papers. Representative work includes small edits, large models, how Wikipedia advocacy shapes LLM values, review guard, aligning LLM-assisted peer review with long-term scientific impact, and RWG bench, evaluating scholarly positioning in related work generation. Trend 7 of 10. Trustworthy and interpretable machine learning. Developing machine learning models that are transparent, reliable, and safe for critical applications. This cluster covers 46 papers. Representative work includes When Do Conservation Laws Survive? Learned Representations, Certified Horizons for Latent World Models, How Complexity Contributes to Learning Opacity in Machine Learning, and Convex-Concave Quadratic Spectral Filtering for Graph Neural Networks. Trend 8 of 10. RL for Complex System Control. Leveraging reinforcement learning to control and optimize complex, dynamic systems across diverse applications. This cluster covers 62 papers. Representative work includes digital twin-driven adaptive sim-to-real alignment via reinforcement learning for vibration-based bearing health monitoring under data scarcity, swarm-inspired generation of collective behaviors in graph dynamical systems, and towards scalable multitask reinforcement learning with large decision models. Trend 9 of 10. Securing and optimizing AI hardware. This trend explores methods to secure, optimize, and ensure the reliable operation of AI hardware and its supporting infrastructure. This cluster covers 64 papers. Representative work includes type-checking project haystack grids using JSON schema and Pydantic, on-device neural architecture search, and unprivileged topology certificates for cloud GPU attestation. Trend 10 of 10. Robust AI for complex data. Robust AI systems tackle complex, noisy, and distribution-shifted data challenges effectively. This cluster covers 79 papers. Representative work includes sport, spherical PSNR optimized truncation for power-efficient 360-degree video systems, Samir, topology-preserving graph miners for thin structure segmentation, and when multi-sensor fusion fails to generalize, cattle posture classification under animal level and temporal distribution shift.
That's all for today's ArXiv Computer Science Daily. If you found this helpful, please leave a comment, and subscribe for daily paper summaries. See you tomorrow. Thank you to ArXiv for use of its open access interoperability.